Welcome back. We are going to solve a problem for the second order system in which now we are going to apply what we just learned, how to find the natural frequency and the damping ratio. So let's take a look at a second order system. Now remember we had the general form of a second order system, so let me write that down here. G of s was equal to omega n squared, where omega n is actually the natural frequency. That is when the zeta or the damping ratio is equal to 0 and the system is oscillating, right? So s squared plus 2 zeta, this is your damping ratio, omega n times the s plus omega n squared. This is the general form of the second order system. Now, like in problem 2 in your homework, one of the questions that is asking is to find the natural frequency, omega n. So let me write this as natural frequency. So here you are going to find the natural frequency of the problem that is given to you on your homework. And we are going to look at a similar problem too. And in this problem, we are also required to find the damping ratio. Damping ratio. Damping ratio. Now remember, this damping ratio can really tell you whether the system is undamped, underdamped, overdamped, or critically damped, right? If you recall our discussion, that's what we talked about, right? Zeta is going to tell you whether the system is undamped, overdamped, or critically damped, right? So if you recall that from our discussion, we said that when zeta is equal to 0, then it is undamped, it's oscillating. Remember that is undamped. The pictures that we looked at before. And if zeta is greater than 0 and less than 1, then it is underdamped. Underdamped. Now remember, underdamped, it oscillates and then comes back. This is undamped. Undamped means it is oscillating like this. So this is underdamped. Also, we looked at one more condition when zeta is equal to 1, and we call that critically damped. Critically damped. Right? So we have looked at undamped, underdamped, and critically damped. Obviously, we have to look at something called overdamped, and that is going to happen when zeta is greater than 1. So that is overdamped. Alright, so here we know we have a complete picture here. Here's the general format of the system. If zeta comes out to be 0, which is our damping ratio, then the system is undamped, it's oscillating. If zeta is between 0 and 1, it's underdamped, equal to 1, critically damped, greater than 1, overdamped. Okay, so knowing that, let's take a look at a system. So we are going to say that g of s here is equal to, let's say, 36. Looks like a good number. 36, and this is the example problem from your reference book by Nice. So that would be 4.2s plus 36. Okay, so looking at this problem, you can compare it with the standard form of the equation, and with that you can conclude that omega n squared is really equal to 36, right? So if you take the square root of that, you will get omega n is equal to 6. Now remember the unit is radians per second, so omega n is the natural frequency, so that will be radians per second. And if we want to find the damping ratio, we got to compare it with this guy, and you can see 2 zeta omega n in our comparison. This is equal to 4.2. So we are looking for the zeta guy. This will be 4.2 divided by 2 omega n, and we already know this is 6, so it is going to be 4.2 divided by 12. And if you do the math, that will come out to be the damping ratio is 0.35. Now if you take a look at 0.35, obviously 0.35 is less than 1 and greater than 0, so you can predict, or you can say this system that we just looked at is an underdamped system. Okay, so this is an underdamped system. So this will help you to solve problem number 2 on your homework, and in the next video, hopefully tomorrow, is getting kind of late over here, so it's 2:30 in the morning already. So tomorrow I will try to do the stacking time, the rise time, the percent overshoot for the second order system, and that will help you solving in problem number 2. Thank you, and I'll see you